Hey, welcome back. So we're going to look at how to make solutions in this video. And making solutions is something we do in the lab all the time. So for example, maybe we want to make a 1 liter of a 1 molar solution of sodium chloride. And you might say, well, how do we do that? Well, first of all, if we have to translate 1 molar to a conversion factor, that means that there are 1.00 moles of sodium chloride in 1 liter. So clearly we can see if we've got 1 liter, it must contain 1 mole of sodium chloride. So how might we prepare that? Well, if we went in the lab, we couldn't actually weigh out 1 mole. Well, we could weigh out a certain number of grams, but we'd have to convert the grams into moles. And so the way we would do this is we would figure out the molar mass of sodium chloride. If we add up the mass of sodium and the mass of chlorine and we put them together, we get the molar mass, which in this case is 58.44. So we'd have to weigh out 58.44 grams of sodium chloride to be equal to 1 mole. So there we go. So it sounds like we are ready to make the solution. So how are we going to do this? Well, let me just quickly pull up a slide. This is an excellent slide from our textbook here. So what we'd have to do is we'd have to weigh out 58.44 grams of sodium chloride. We'd weigh it out on a balance. And then what we're going to use is we're going to use this thing here called a volumetric flask. And a volumetric flask has one thing going for it, and that is there's a single mark somewhere up the side, and it says when you fill me up to here, I contain exactly 1 liter. So the thing is you would put the sodium chloride in first, and then you would add the water second. And normally what you do is you'd add it up part of the way, and then you'd cap it, and you shake it, and you dissolve it, and then you'd fill it up to the line. And at that point there, you would have a 1 molar sodium chloride solution. Now, this doesn't seem too bad, and it's one of those things that it sounds kind of obvious, but another obvious way to do it is actually wrong, and the obvious way that's wrong is to fill it up with 1 liter of water first, and then add the 1 mole or the 58.44 grams of sodium chloride second. And the reason that that doesn't work is that as you add the salt, the overall level can go up or can go down or may stay the same. So some solutes, when you add them, it actually causes the water molecules to squeeze together more tightly. The volume would drop. A lot of times, though, that the water molecules kind of pushed apart, so the volume would increase. And every now and again, you get one where it doesn't change at all. And of course, in the case of salt, when you add it, the volume would go up. So you would actually have 1 mole dissolved in a larger volume. So remember, molarity is the number of moles of solute divided by the number of liters of solution, not just the solvent. So that's how you make a solution. All right, so here's a good problem to try. So how would you make 250 milliliters of a 3 molar solution of potassium chloride? And first off, you have to know, well, how much potassium chloride are we talking about here? So we can do this with a conversion. So 250 milliliters, we can convert to liters. Remember, there are 1,000 milliliters in a liter. Units cancel and give us liters at this point. And the very last thing is to remember 3 molar is a conversion factor. It means that there are 3 moles of potassium chloride in every 1 liter. And so if we go ahead and we multiply that through, we get 0.75 moles of KCl. In fact, our calculator won't show us the last digit of 0 there, but remember that this has 3 significant figures. This is exact. This has 3. This is exact. So in actual fact, this is missing 1 digit. So we should probably go ahead and write 0.750. Now, what is that in mass? So we have to go ahead and remember that in the lab, right, we're going to weigh this stuff out. So we don't have balances that read off directly in moles. So chlorine is 35.45, potassium is 39.10. So if we sum that together, let's see, both of those are to the second decimal point. So we're okay to show both of these. 9 and 5 is 14, carry the 1. So that's 74.55 grams per mole. So if we wanted 0.75 moles of KCl, right, we would have to multiply that by the molar mass. So the molar mass, 74.55 grams, go on the top, and the 1 mole goes on the bottom. And at the end of the day, we would have 55.9 to 3 significant figures grams of potassium chloride. So we'd have to weigh out that much potassium chloride. So how would we make the solution? So let me just pull this up again. What we'd have to do, and there's a question I think in the lab manual that basically asks you to calculate this. What we'd have to do is we'd have to take out a 250 milliliter volumetric flask. And the 250 milliliter volumetric flask basically has a mark on the side, and 250 mil volumetric So all its job is in life is assuming that you've got or is assuring that you've got that total volume. So what would you have to do? So first of all, you'd have to weigh out 55.9, grams of potassium chloride. And then secondly, you would have to put it in this volumetric flask. You'd have to quantitatively transfer it. So quantitatively just means that you don't drop any or spill any. And then you would essentially add pure water. In the lab, we often use deionized or distilled water, and then we would dissolve it, give it a shake with the top on, and then 5 we would bring to volume. So what that means is that you would go ahead and you continue adding water until you got up to this mark right here, and then you would cap it again and shake it up. So that would be the way you would make it in the lab. Now these volumetric flasks, so it turns out that they come in various different classes or grades, and so very roughly we can assume that when we have a volumetric flask, it's something like good to 4 significant figures. So we can assume it's something like that. And I believe that in actual fact, if it's a class A, it's actually good to, let's see, I just pulled this out of my analytical textbook. It's good to 0.12 of a mil. So very roughly, we can say it's good to about 1/10 of a mil. So nothing is perfect in this world. Class A, so there's this sort of international agreed upon, system. And Class A is the best, Class B is the next best, and then student grade is actually not classified at all. And so when we have, say, a 100 mil flask, it's good or it's plus or minus to 0.08 of a mil. So very roughly, it's 100.0. And when we get to the larger capacities, then maybe it's only good to 0.5 mil. So very roughly, you can assume it's good to 0.0 of a milliliter. So these volumetric flasks are absolutely wonderful. They contain a consistent amount of volume, and we use them all the time in the lab to make solutions. Awesome.